Hello, this is Mrs. Taylor, and I'm going to introduce you to related rates problems that involve cones. There are two types of problems. There are problems where you have a substance that's falling into a cone shape, like let's say gravel falling off a conveyor belt. And then you also have problems where you have a cone-shaped tank that's being filled with something. So the material that's filling the cone is taking on a conical shape as well. And so what I'm going to go over with you is a type of problem where you have a tank being filled. The problems that involve something falling into a cone-shaped pile are going to be solved a little differently. So in this problem it says a conical tank with vertex down is 10 feet across the top and 12 feet deep. If water is flowing into the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the water when the water is 8 feet deep. And so the first thing we want to do is understand the problem. And what I like to do is make a list of information that they give me. So if I list out all of these numbers that they're providing and what they represent, I know that if the conical tank is 10 feet across, that's a diameter. Because if you think about it, a cone's base is a circle, and so across the circle would be a diameter. So the radius would be 5 feet. And the reason why I chose to list it as radius is because I know I'm going to be working with some formula for a circle or a cone, which only involves radius, not diameter. Okay, so 12 feet deep, that's the height of the tank. When you talk about depth, that's the same thing as height. They tell you that the water's flowing at a rate of 10 cubic feet per minute, so that would be a rate of change with respect to time, and it's a measurement of volume because it's cubic feet, so dV over dt equals 10 feet cubed per minute. And then it says find the rate of change of the depth of the water. So I'll note that, remember depth is height, so rate of change of the depth of water, dH over dt, put a question mark there because that's what I'm looking for, when the water is 8 feet deep. Again, depth is height, so h equals 8 feet. And I'm looking for rate of change of height, but they give me the rate of change of the volume. So I know I'm going to need the volume formula for a cone. So volume equals 1/3 pi r squared h. And the other thing I'm just going to note here is that this is a problem where they're wanting you to find the rate of change of the depth of the water. And so I'm just going to mark that this rate of change of volume and the rate of change of the height is for the water, not the tank itself. So that's what makes this different from a problem where you have a cone-shaped pile. Because we're not looking for the rate of change of the tank, we're looking for the rate of change of the water. And so that's going to be really important when we're working through this problem. All right, so the next thing we need to do is draw or sketch a model of this situation. So what I have is I have a conical shape with vertex down, so the point is downward. It's 10 feet across, 12 feet deep, and it's being filled with water. And if you think about it, the water itself is going to take on a cone shape, and it's going to have its own radius and height that's different from the tank itself. And that radius and height are always going to be changing. So if I am given dV over dt, and I'm looking for dH over dt, then I know that this volume formula is going to give me what I need when I take the derivative because it has both the variable v and h in it. However, it also has that variable r. And if I took the derivative of the volume formula as it's written with respect to time, when I took the derivative of the variable r, would have dr over dt. And they didn't give me a measurement of dr over dt. So what that means is that I need to use substitution so that I eliminate the r so that I don't end up with dr over dt, which I don't have a value for, and so I can't solve the problem. And so the relationship that you're supposed to use is the relationship between the rate and height, or radius and the height of the water, and the radius and the height of the tank. Think back to geometry. The radius and height forms a right triangle with this lateral edge here. This is the slant height down the side of the cone. And then the cone itself, if you think the height straight through the radius of the tank and then this outer edge here, those both form right triangles. And it's a mathematical fact that all right triangles are similar. So what that means is that the radius and height of the water is proportional to the radius and height of the tank itself. And so if that's true, then I can create a proportion that relates radius and height of the water to radius and height of the tank. And so that would be radius to height of the water is equal to the radius of the tank, which would be 5, the height of the tank, which would be 12. And now that I have a proportion, I can cross multiply and get an equation that relates radius to height so that I can use substitution in my volume formula. So cross multiplying would give me 12R equals 5H. And solving for R, I'd divide both sides by 12, so R would equal 5/12H. So now that I have that, I can plug 5/12H into my volume formula. And then I can simplify by squaring 5/12 and then h squared. H squared times h would be h cubed. And remember with these problems that you don't have to struggle to simplify these numbers. You can leave this as 1/3 5/12 all squared pi h cubed, because remember all of these are just constants in front of your variable. So when you take your derivative, you just multiply all this by 3, subtract 1 from the exponent, and you don't have to simplify. So remember that on tests and exams. Don't waste time simplifying, just write out the values. So if I take the derivative, remember it's with respect to time. My derivative would be dv over dt equals 5/12 squared pi h squared dh over dt. If you think about it, 3 times 1/3 is just 1, and so that kind of cancels out or eliminates, and you're just left with 5/12 squared pi as your constants. Now, I am given dv over dt, so I can plug that number in, and then I would be able to now plug the height of 8 feet into my equation and find out what dh over dt is. And just to go back a little bit, one thing that I didn't discuss is the fact that we don't want to plug 8 feet into the volume before we take the derivative, because 8 feet is dependent upon time. It's a changing measurement. And so you don't plug any measurement in that's changing until after you've taken the derivative. Okay, so plugging in all those numbers and solving for dh over dt, my final result would be dh over dt equals 10 over 25 over 144 pi 8 squared. And just to kind of give you an idea of where that came from, because it's kind of a very messy number. If you think about it, dv over dt would have equaled 10. You would have divided by these constants here. And for whatever reason, I squared 5 and 12 to get 25 over 144. And then remember, h was 8. And so you could also divide by that as well and get the 8 squared. And so this is a perfectly acceptable way to present your final answer, as long as you include units. Without the units, you don't get full credit. And you have to think through the units. So this is a measurement of height. Height is a one-dimensional unit, one-dimensional measurement, and so that would be feet. And it's with respect to time, and our measurement of time in this problem was minutes. So feet per minute would be your units for dh over dt. And so that is how you would complete a word problem for related rates that dealt with a cone-shaped tank being filled with some substance.